Have you ever noticed how some chemical reactions seem to just stop? You mix everything together, you're expecting it all to turn into your final product, but instead, the reaction gets partway there and just stalls. Well, it turns out it hasn't failed at all. It's actually reached a perfect state of balance. And today, we're diving into the really powerful world of chemical equilibrium.
Okay, so let's jump right in with a massive real-world example. This is an ammonia plant. It literally takes nitrogen from the air we breathe, combines it with hydrogen, and makes the ammonia that goes into fertilizers. But here's the puzzle. The reaction that makes it, called the Haber process, never actually uses up all its ingredients. It just stops with tons of nitrogen and hydrogen left over. So how do chemists actually get enough product to, feed the world? That's the mystery we're going to solve.
To get to the bottom of this, the very first thing we have to get our heads around is that chemical reactions aren't always a one-way street. Nope, a lot of them can go forwards and backwards.
And that brings us to our first big idea, the reversible reaction. Seriously, just think of it as a chemical two-way street. The products that get made can turn right back around and reform the original reactants. It's this constant back and forth with both things happening at the very same time.
Now, what's so cool about this slide is that it lets you see this idea in action. On the left, that's blue hydrated copper 2 sulfate. If you heat it up, you drive the water out, and you get that white powder on the right. That's the forward reaction. But, and here's the cool part, if you add a drop of water back to that white powder, poof, it turns right back to blue again. That's the reverse reaction. See? A perfect two-way street.
And because chemists, we love to be efficient, we have a special symbol for this. The double arrow. So anytime you see this little guy, it's a huge clue. It's telling you, hey, this reaction is reversible. It's going both ways at once.
So we have this two-way street, right? But what happens when the traffic going in both directions becomes perfectly exactly equal? Well, that's when we hit the balancing point.
We call this state dynamic equilibrium. Now, that word dynamic is absolutely crucial here. It means things are still happening. Reactants are still turning into products, and products are still turning back into reactants. But, and this is the key, the speed or the rate of the forward reaction becomes exactly equal to the rate of the reverse reaction. So even though molecules are constantly changing teams, the overall amounts of everything just stay the same.
Let's zoom way in, down to the molecular level. What we're seeing here is a mix of hydrogen, iodine, and hydrogen iodide gas that's hit equilibrium. All three types of molecules are just bouncing around in there together. They're not just sitting still. At any given second, a hydrogen and an iodine molecule are linking up, while somewhere else, a hydrogen iodide molecule is breaking apart. It's like a perfectly choreographed, non-stop dance. And this right here is one of the most powerful ideas about equilibrium. Just look at these two graphs. On the left, we start out with only reactants. You can see their concentration drops while the product concentration goes up until they all flatline at that stable equilibrium point. Now look at the right. Here, we start with only the product. Its concentration falls as it breaks down into reactants, and what do you know? It levels off at the exact same concentrations. It doesn't matter where you start. Equilibrium is this fundamental, stable state that a reaction wants to get to.
But there's a catch. Of course there's a catch. This whole delicate balance can only happen in what we call a closed system. For instance, if you heat calcium carbonate in a sealed jar, it'll reach equilibrium. But if you do it in an open beaker, the carbon dioxide gas just floats away. And if one of the products is gone, well, the reverse reaction can't happen, can it? So the forward reaction just keeps going until all the reacting is gone. The takeaway? For equilibrium to work, nothing can get in or out.
So we have this nicely balanced system. What happens if we try to mess with it? What if we try to disturb it? Well, it turns out there's a rulebook for that, and it's all about resistance.
This is the golden rule, my friends. It's called Le Chatelier's principle. And to put it simply, it means that a system at equilibrium will fight back against any change you make to it. It's going to shift its balance to try and cancel out whatever you just did. It's basically the chemical version of a system saying, hey, I was comfortable, and I'm going to do whatever I can to get back to that comfortable spot.
And this is where it gets really useful for us, because if we know the system is going to fight back, we can actually predict how it's going to fight back. We can learn how to tip the scales in our favor. It's actually pretty simple.
If you dump in more of a reactant, the system responds by shifting to the right to use up that extra reactant and make more product. On the flip side, if you add more product, the system shifts to the left to get rid of that excess. It always moves to oppose what you just did. All right, next scenario. Let's say we're dealing with gases. What happens if we crank up the pressure?
So pressure is just gas molecules smacking into the walls of the container. If you increase that pressure, the system wants to relieve it. And how can it do that? Well, by reducing the total number of gas molecules bumping around. So the equilibrium will shift to whichever side of the equation has fewer moles of gas. Simple as that.
This table makes it crystal clear. Let's look at our ammonia reaction. On the left side, we have 4 gas molecules total, and on the right, we only have 2. So if you increase the pressure, you push the reaction to the right, toward the side with fewer molecules. You make more ammonia. But for that second reaction, it's the opposite. The right side has more molecules, so increasing the pressure actually pushes it to the left.
And what about temperature? You guessed it, the system fights back against that too. If you heat the system up, the equilibrium will shift in the direction that absorbs that heat. That's the endothermic direction, to try and cool things down. And if you cool the system down, it'll shift in the direction that releases heat, the exothermic direction, to try and warm itself back up. Again, it always opposes the change.
Okay, this is a really common question. If we add a catalyst to make everything go faster, does that actually change the final balance? And the answer is a very clear no. A catalyst is kind of like a chemical matchmaker. It helps the forward reaction happen faster, but it also helps the reverse reaction happen faster by the exact same amount. All it does is help the system get to its equilibrium balance point much, much faster. It doesn't change where that balance point actually is.
Okay, so we've got the rules of the game now. We know about concentration, pressure, temperature, and catalysts. So let's go back to our ammonia plant and use this knowledge to become the master of this reaction.
We are right back where we started. But now, we have the tools, we have the playbook. How do we force this equilibrium to give us the absolute maximum amount of ammonia?
Here's the strategy, and it's built entirely on the Chatelier's principle. First, chemists use incredibly high pressure. Why? Because the product side has fewer gas molecules, so cranking up the pressure shoves the equilibrium to the right. Bam! More ammonia. Second, temperature is a trade-off. The reaction is exothermic, so a low temperature would be best for the equilibrium. But then the reaction is painfully slow, so they use a compromise, a moderately high temperature to get a decent speed, and they throw in a catalyst to make it even faster. And finally, here's the cleverest trick of all. As soon as ammonia is made, it's cooled down, turned into a liquid, and drained away. By constantly removing the product, you're constantly forcing the equilibrium to shift right to try and replace it. It's genius. So, you see, chemical equilibrium isn't about reactions stopping. It's about them reaching this incredible, dynamic, stable balance. And by understanding the rules of that balance, we can actually tip the scales in our favor. So now that you know the rules, think about it. What other industrial or even natural processes could you control by understanding the art of this balancing act?